Good morning, everybody. Welcome to Monday Zoom. And I hope you got my email about test 1 being moved to next Wednesday. I have an opportunity to celebrate my daughter's birthday in Georgia while camping this weekend, and I will be very tired on Monday. Enough said about that. We're going to move on over. Do I have audio? We do. Move on over, continue our discussion of chapter 16. We're going to finish it within an hour, I believe. We'll see. I'm always ambitious with my time estimates. And here we go. We're going to look at reactions. Of the alpha carbon. Okay. Pen on. Alpha carbon. And I'm pretty sure you all remember that one is the one that's one away from a carbonyl. And for aldehydes and ketones, if there's a hydrogen there, it's called an alpha hydrogen. And it's a pKa of roughly 20. This theme runs throughout this whole course. It's an important alpha hydrogen. We're going to do tautomerization. This is not new. This was first encountered in chapter 7. I believe we were doing acid catalyzed hydration of alkynes in the presence of mercury 2+ ion when we first saw tautomerization. And then in the very next section, during hydroboration and oxidation of alkynes, we saw the base catalyzed version of tautomerization. And what goes on here is there's an acid-base pair. In the acid version here, I've chosen to use para-toluene sulfonic acid, aka HOTS, and its conjugate base. And in the base catalyzed version, I'm using hydroxide and water. They are both conjugate acid-base pairs. This is the base here, and this is the acid. Over here, we have the base here and the acid. In this mechanism, we take the alpha H with the base. I would think that that is the last arrow. I never require you to put numbers on arrows, but given this wording, acid catalyzed, it should make sense that the first arrow, the lead arrow, would be reaction with that strong acid. And that's what draws in this second and third arrow. And then you have your enol intermediate, a well-named functional group with an alkene and an alcohol. And the reverse tautomerization happens. We have the base grab the H from the all portion of the enol, the alcohol, and resonate to the pi. Pi picks up a proton and puts an alpha H back on the alpha carbon. Once again, acid here, base here. Here I would have to think the lead arrow would be this one, which causes this. And then you would have a carbocation here, which would easily be neutralized here. And once again, you do not have to put these numbers on here. So don't worry too much about the numbers. In the base catalyzed tautomerization, you don't have to show the resonance step. You can just dump the electrons onto the alpha carbon. I know this is not the most stable resonance form, but it's the one that puts a proton on the alpha position. So we don't have to resonate to make an ene and an O minus. We'll just go from this resonance form. And this is true of any reaction involving resonance. You can choose the resonance form that gets you there faster every time. And here's an acid-base reaction to put the proton back on. And the whole gist of these lines up here are that if you start with a pure enantiomer of a chiral molecule that has a specific stereocenter on the alpha position, and that alpha position has a hydrogen, you will no longer have a pure enantiomer if you present this molecule with a strong acid. It will undergo what's called, and the magic word is in the title, racemization. You remember a racemic mixture is a 50-50 mixture of two enantiomers. And when you started with this pure molecule. Generally, pure chiral molecules are fairly expensive entities. And then if you mistakenly put in the strong acid, you will end up with a mixture that is 50% the one you started with and 50% of the other enantiomer, and you can't stop this from happening. And now it's not valuable anymore. You have a racemic mixture, and then you've got to invest all that time you invested to get the pure enantiomer back. If you want to review that, that's in chapter 3, separation of enantiomers. But it was not a simple process. I hope you remember that. And you caused racemization. Same story if you present a pure enantiomer with a strong base, you're going to get a 50-50 mixture of the pure enantiomer you started with and its enantiomer. And let's relate this to the importance of chirality. The importance of chirality in medicine. We've got the molecule thalidomide. Now, there was an essay on that in the first textbook, and Dr. Frances Kelsey prevented a lot of damage happening from this drug in the United States because she wouldn't let it come to the market. An example of regulations when they're done well. Even after the whole disaster was over and it was no longer used as a medicine to give to pregnant women, and then learning that it was only one enantiomer that caused the birth defects. Even after that, that was no consolation, because even if you administered the pure drug that was beneficial to the women, because your body contains acid-base conjugate pairs, and this is an alpha position on the drug thalidomide, even if this was the beneficial version of the molecule, enzymes and their conjugate acids would tautomerize the racemization of the good form to a 50-50 mixture of the good form and the bad form. And get used to these short forms as we progress through this course. We're leading towards biochemistry, which is just organic chemistry with biological molecules. You'll see the mechanism here is identical to the one above. This is the base. Here's the base form of the enzyme. This is the acid form of the enzyme. Here's the acid. These arrows are identical. And these arrows are identical here to what's going on up there. So that's a drug that even administering only the beneficial isomer would not have helped. Enough said about that. Let's do our own quick version of this mechanism before we take a break. Let's look at this one here. And let's treat it with, let's do a base version. So if you were asked to do this mechanism on a test, I expect you to do everything down here. Trying to get down on the lower portion of the screen here. First step, cross off that spectator. Don't forget, you need a lone pair. You also need the charge. If you don't put the lone pair, I won't know where your first arrow is starting. If you don't put the charge, you'll lose a half point. I'll do this version where I do resonate. I gave a whole speech, but there was no visual for what I was talking about. So on the one on the top of the screen, I did not resonate up to the O minus. Down here, I am resonating to the O minus. Doesn't really change the mechanism, except you have to draw the resonance form. And you'll notice this is an ene all conjugate base called an enolate. Now, you don't have chapter 19 yet, but when you do have it, that's the title of the chapter, enolates used in organic synthesis. So yeah, this alpha carbon stuff's real important. That whole chapter is about the alpha carbon. And lone pair. What's going to put a proton back on the alpha position? The conjugate acid of HOH. Either use this one here or realize that you made one. Get some colors going here. And you can use that one. Resonance back. See, I had to resonate here and then unresonate. That's not unresonate, it's resonance. Undo the resonance that I did earlier. And I end up with my racemic mixture. 50% here, 50% here. Why is it 50%, 50%? We haven't addressed that question. That'll be our last question. That's a short segment if I stop. Maybe we won't stop. It's 50% because this enolate, if you look at the geometry of the atoms, and there's how many atoms here? Carbon, carbon double bond with 4 things attached. All 6 of those atoms are in the same plane. And when they're in the same plane, it's flat. So an approaching water can either approach from the top of the molecule to create this, or it could approach from underneath the molecule and you'd be going backwards to here. And there's no preference when you have a flat structure. It's not like there's a backside or anything. It's flat. And that's that. And we'll go to the next one and see if it relates very well to this, then we won't start a new segment. And it does. It's the same thing. So we'll do this screen and then take a break. We've got the same thing going on here. We're calling this base catalyzed deuteration. Deuteration is nothing more than adding a deuterium. And I hope you remember, and if you don't, here it is. A deuterium, the symbol D, is really a hydrogen atom with an extra neutron in its nucleus. So a hydrogen atom has a proton in the nucleus. That's why normal hydrogen weighs 1 gram per mole. And if it has an extra neutron, it has a mass of 2. And that's deuterium. The book does discuss how replacing a hydrogen with deuterium affects reaction rates. And this is how mechanisms are studied in research. I will never test you on that, although it's very interesting. It's more of an intermediate level organic chemistry discussion. But we are responsible for this mechanism because it's the same as the mechanism we saw on the previous page, except we're using deuteroxide ion, deuteroxide, just like we called it hydroxide when it was a hydrogen. It's deuteroxide when it's a deuterium. And this is DOD, also known as heavy water. Or you want to get fancy, you can call it dideuterium monoxide. And it's the conjugate acid of OD minus. We're protonating it. And now you've got 1 deuterium where you used to have 2 hydrogens. if you want this process to go to equilibrium to this product, just make sure you have a large excess of these two things. We know Le Chatelier says we always shift away from excesses. And if you want to make sure there's all the alpha positions are occupied by deuteriums, just use excess of those two. And you will force this equilibrium to the right as well. It's the same mechanism again, isn't it? And once again. And the same story exactly holds true for the acid catalyzed deuteration. If you want to make sure you get a nice yield, and this molecule only has one alpha position hydrogen, so you're only going to get one deuterium on there. If you want to make sure you get 100% yield, no problem, just use a large excess of the deuterated version of sulfuric acid. Here's its conjugate base, which is always present when we have a strong acid. It's assumed you know that you have a large amount of this as well because it's a strong acid. So that's why I never draw these on tests, the conjugate bases of strong acids, yet you are free to use them anytime you wish. And this is the other mechanism from the previous page. The base grabs the H, sigma becomes pi, and you get an OH enol. I guess you'd have to call it a deuterol, deuterol. And then the reverse tautomerization gives you your deutero species. And we got a nice little summary down here. You can do the acid catalyzed version or the base catalyzed version. Aldehydes, if you have ketones that have H's here and here, and you push this thing with a large excess of either this or this, then you can deuterate every position that's an alpha position that had a hydrogen previously. You can't do it unless there's a hydrogen there, right? So hydrogen deuterium exchange would be a good summary of this. Hydrogen deuterium exchange, because that's exactly what's going on. And that brings to a close this segment of today's lecture, and I will see you shortly.